Guys, first lesson from this unit basically talked about extremes. Agreed? We talked about absolute maxes, we talked about absolute mins. And in order for us, we also talked about locality, right? We also found some local mins and maxes. And what did we say about where these extremes can occur? They can occur at endpoints of a closed interval, right? They could also happen at critical values. And what did we say were critical values? Where a derivative doesn't exist, where a derivative equals 0, right? And endpoints would be critical values as well, right? Within a closed interval, okay? So now we're gonna keep taking that concept, guys, and applying some layers to it, okay? And the first layer here is a guy Roll, all right? He had a theorem, and what he said was the following. If a function is continuous on a closed interval, a to b. So basically, what does that mean? Well, here's a, here's b, here's a point, here's a point. Continuous. So don't pick up the pen, right? So maybe it looks something like that. And if f is differentiable on the open interval a to b, then f of a has to equal f of b. What does that mean? What does that mean? Well, there are three different scenarios. Here's a, here's b, right? Does this satisfy all three of those conditions? Is it closed from a to b? Yep, what's on the ends? Closed circles, right? Okay. Is this differentiable at all points between a and b? Sure, okay. Is f of a equal to f of b? Is this point equal to this point? Yes. So basically what this theorem says, guys, is there has to be some place where the derivative equals 0. Well, what's the derivative at any point along this? 0. Here's f of a, here's f of b. Closed? Continuous? Are these in the same positions as same y position? So check it out. Is there a spot where the derivative equals 0? Right? Here's a spot. Okay. Maybe it looks like this, in which case there can be more than one spot. Or maybe it looks like this, right? But there's no way that it doesn't equal 0 at least once. Can we all agree with that? Okay. And he did some really cool proofs of that. So here's what I want to do. Here's a function. I want to know if Roll's theorem applies. Well, if it applies, what has to happen? Condition 1. It has to be continuous. Guys, is this going to be a continuous function? Yeah, it's just a power function, right? So f of x is continuous. From -2 to 2. Is f of x going to be differentiable? Well, can I take a derivative of this? Sure. Yeah, what's the derivative going to be? 4x cubed minus 4x. All right. So differentiable. I got a derivative, right? F of a has to equal f of b. All right. F of a, which is going to be f of -2, What's that going to give me? That's going to give me negative 2 to the 4th. Oh. That's going to give me 8. Promise. Swear. All right, so that's one endpoint, right? So now, Brandon, what has to be true? It has to be true at this endpoint and at the other endpoint that I'm at the same y position, right? So when I plug in 2, I also need to get what? 8. And I promise you, swear that you do. You get 8. So, Lexi, the function is continuous on the interval. The function is differentiable. And f of negative 2 is the same as f of positive 2. All three things work. Rolle's theorem applies. What does Rolle's theorem say? It says there has to be a point on this where the derivative equaled what? 0. Equaled 0, right? So Rolle's theorem applies. And there has to be a point where that's true. There's actually 3 of them. Okay. That kind of makes sense, right, guys? Like, there's no way that I can go from one position here to here and create a function, right? If I told you to come up here and connect the dots, there's no way that you can do that continuously. Actually, don't do that, but there's no way that you can do that without there being a horizontal tangent, right? There's just no way. Do we all agree? So now we're going to expand that theorem, okay? And now we get the mean value theorem. And the mean value theorem actually becomes a really important thing for us to understand, okay? And here's what it says, all right? Evan, we're going to take this a step further because most of the time, this point and this point aren't going to line up, right? Like, it was really nice for Rolle's theorem that they were in the same y position, right? Well, now that's not true. So if that's not true, are they going to have a, is it going to be true that, so let me do it this way. Here's the point, and here's a point down here, right? Can I get from here to here without having a horizontal tangent? Easily, right? No doubt about it. So Rolle's theorem doesn't apply to this. Do we agree? And the reason it doesn't apply is because these 2 points are not in the same y position. Everybody agrees with that. So what this new guy came up with is this cool idea. If I connect these 2 dots, I get a secant, don't I? I get a secant of this curve. Why is it a secant of this curve? Because it touches the curve in how many spots? 2. Well, here's what this new guy said. This new guy said, if this has a slope and there's a function that connects these 2 points, then there has to be tangent points that have the same slope as this secant. In other words, do you agree that the derivative right there is parallel to that? And same is true there, isn't it? So there has to be at least one value, right? So there's my two endpoints, which are not at the same y position. There's a line of secant, right? Here's a curve. In this case, I have a tangent line that must exist that's parallel to that secant. And here's similar to what I just did over there. So do we see how the theorem works? Okay. So we want to know if the mean value theorem applies, right? And again, let's go back to the conditions for it to apply. The conditions for it to apply are less rigorous. All right, Evan, they are less rigorous because all I need to have now is what? A closed interval and a differentiable function. If I have those two things, then the mean value theorem applies. So less stringent because what? The y values don't have to agree. Okay? And what the theorem now says is, okay, well, if I found the slope between those two endpoints, then the derivative has to equal that slope at some point, at least one. Okay? So let's do it. Determine if the mean value theorem applies. Well, does the mean value theorem apply? What do I need to have? A continuous function on a closed interval. Do I have that? Yes. And I need to have a function that is differentiable on that open interval from 0 to 2. Is it differentiable? Of course it is, right? Okay, so it's going to apply, all right? So here's what I need to do. I want, guys, I'm gonna do this graphically really quickly. Evan, this is a third degree polynomial, right? So maybe it looks, again, I don't know what it looks like, but maybe it looks like this. So here's what I'm saying. I'm saying that there is a point right here, which is f of 0, and there is a point right here, which is f of 2. With me? Now, do you guys all agree that I can find that slope? Yes? All right, so I want to find the slope between let's see here, the point between those two things, right? 0f of 0 and 2f of 2. So 0f of 0 is 0, 0. And this is going to be 6, 2, 6. All right, so what's the slope between these 2 points? The slope is equal to 3. So what did we just find, guys? We just found the slope of this what? Dotted green line, right? This secant that exists between these 2 points. Is that cool? What does the mean value theorem say? It says there has to be at least one spot on this curve where what? Where the derivative has a slope that is the same as that secant, right? Okay, so let's take our derivative. Our derivative's 3x squared minus 1. And the mean value theorem says that somewhere the derivative has to equal 3. Right? The derivative has to equal 3 by the mean value theorem. So what do we get here? We get x squared we get that. Now, one thing of note here, guys. I can't have the negative answer. Why? It's not in the what? It's not in the interval, right? So remember that I only want the solutions that are in this interval of space, right? So here we need to reject that, right? So we only have one solution, and that's the positive radical 4/3. Right? Kind of cool, right? Now, it doesn't seem all that cool right now. You'll see how it will become cool as we move on. All right? Yeah, go ahead. The x, this one, I just divided by three. Yeah, this was just continuous. Sorry. With the help of your calculator's ability to graph zeros, determine all the numbers that satisfy the mean value theorem. Okay, good. Let's have the calculator help us here, right? And this is going to really like sort of bring home exactly what this is doing right now, okay? Here's what I need to know. Continuous function, closed interval. Can I take a derivative? No issues with that? Agreed. Okay, good. So will it apply? Everything seems awesome. So what do I need to do? Well, I need to figure out the slope of that secant, don't I? Right? I need to find the slope of that secant. So what I'm going to do is I'm going to find the slope between -1, f of -1, and 2, f of 2. All right, so I'm going to do that. It says we can use the calculator, so all right, let's do it. This actually does look a lot better. Pretty bright now. Maybe it's almost too bright. No. All right, I like using this. This is one of those things, guys, we haven't practiced this very much. As we do exam prep, we're going to practice the heck out of calculator stuff and how quickly we got to be able to type and move through that thing. But this is one of those things that'll help you get through questions quicker when you don't have to retype things. Defining them makes it really, really quick and easy. All right, so there it is, right? And now what am I going to do? I'm going to find the slope, right? So literally, like, these are some of those little tricks that we're going to work on. Right? And that should give me a slope, shouldn't it? So there's my slope. Slope is 4. And then what do again, let's talk about what's happening, right? This is the what? The slope that exists between f of -1 and f of 2. Agreed? So now what do I know? I know that by the mean value theorem, when I take the derivative of this, there's at least one point that has the derivative equal to what? 4. Yeah, exactly. Yep. So since the mean value theorem applies, there's at least one solution where the derivative equals 4, right? That's what we're trying to accomplish, right? There's at least one solution where the derivative equals 4. So our derivative is 3x squared plus 4x minus 1. So there has to be at least one solution where this equals 4. Oops. So I get that. And again, it's a calculator problem, right? So use your calculator's ability to find zeros. I just want to find the roots of this, right? So how do we do that? How about polytools, right? Find roots. Second degree polynomial. 3, 4, negative 5. There you go. All right. Negative 2.11963. Bang. That's an 8.63. Hey, really quickly though, what's our issue? Can't have the negative 2, right? Because it's outside of the interval. Boom. You guys want to see what this actually looks like? So here's what we really just did, okay? So there's the graph, right? Now, what did we just say? We said that there is a point. What was the interval? From -1 to 2. Okay. Let me zoom out a little bit. Zoom out a little bit. All right. So what I'm saying is what? If you were to connect a dot or connect the lines, connect the dots from here to here, let's do that. Then there's a point that exists at 0.7863. What was it? 863. Right there. And what's true about that point? If I were to find the slope of this point as a tangent, analyze graph, give me the derivative at this point, what did it say it was? 4. Okay, let's ask the calculator to give me the slope of this line. And there it is, right? And that's what we just accomplished, right? That's what we just accomplished. We got a good visual of it all. Right? Now, does that mean if I were to change the interval, right? Well, there could be more than one answer, right? So had I said the interval goes not from -1 to 2, but -3 to 2, then we would have had another answer, and that answer would have been that -2 point whatever. Okay, so yes, the interval of space matters. Okay. Oh wait, but that would actually change the slope, wouldn't it? If you change the interval. So it's all relative to the interval anyways. So, nonetheless. Go ahead, do this example 4. And this question sort of like engages the little minor details, doesn't it? And if you found yourself flipping back, then that was smart, right? Because what does Rolle's theorem and the mean value theorem say? It says that there has to be a solution that exists not on the closed interval, but on the open interval. In other words, when I find the answers to this, they can't be at the actual endpoints. They can only be within the endpoints. So when I do this problem and I get a solution of 0 and 2, I have to reject the answer of 0. I have to reject the answer of 0. Because it's a quadratic, right? Anytime I got a square, I'm always going to move everything over. Actually, anytime I have anything other than a linear equation, I'm going to, right? Yeah, so the theorem's really specific in that when I do this, right, there has to be a value guaranteed within the interval, but not on the interval, right? So this point and this point are not included within the solution. I want to, you got it? All right. I want to give you a reason why though. Like I want to be like, because yeah, but I want to give you a better reason than because, but I think right now because is going to have to suffice. What do you think is going to happen here in example 5? Probably going to have a case where the mean value theorem doesn't apply, right? Because clearly if we're talking about cases where it does, then there's got to be somewhere it doesn't. And here's what we know. Guys, talk to me about this function. Is it a continuous function? Yes or no? No, right? So f of x is not continuous at x equals 1, right? Because what's at x equals 1? An undefined vertical asymptote, right? And so the mean value theorem does not apply on the interval -3 to 5. Just gonna say this. Go ahead.
If it was that same function but on the interval of like 2 to 5?
Yeah, so absolutely. So if I had said let's do this from the interval 2 to 5, you would say, great, let's do it. Because it is continuous on that interval, right? It's not continuous overall though, is it? Okay. So in this case, it would not apply. Cool. All right. What about B? How could I rewrite that, first of all? I don't like fractional exponents. They confuse me unless I'm doing derivatives. That's the same thing as the square root of what? The cubed root of x squared. Good. All right, so that's a way that I can write it. Now, when I write it like that, it actually helps me analyze what's happening. If I plug 0 into this, okay? Right? What do I get when I plug in 0? I get 0, yeah. What if I plug in 1? I get 1. What if I plug in 2? Cubed root of 4. What if I plug in negative values? I can plug in negative values, yeah, sure. What does this look like graphically? What does this look like graphically? Oh, remember, anytime I have one of these, anytime I have a fractional exponent, what often happens? Close. Not asymptotes. We often see cusps, right? When we see fractional exponents, we're often going to see a cusp. That's that sharp point. So watch what happens when I graph this. Right? And that's on, we're looking at an interval from what? From -3 to like here-ish, right? So within that, what happened? Is there a point that is not differentiable? Yes. So does this theorem apply? No, right? Now, this is one of these things, guys, that as we go through the year, I'm going to keep pointing out when you see fractional exponents, right, you're often going to see cuffs, right? And so this, the mean value theorem, so since f of x is not differentiable at 0, the mean value theorem does not apply from -3 to 3. And Emma was really awesome because, like she pointed out, like this statement here, this interval at the end is important, right? Like this would apply if it was 1 to 3, wouldn't it? Right? So again, you got to make sure that the issue occurs within the interval and that you state where that interval was. It's going to be this. You're looking for those fractional exponents. When you have those fractional exponents or something that looks like this, you're going to have cusps. I don't think so. I think for the purposes of what we're doing, you're going to have cusps. Yeah. Yep. And we'll keep hammering this as we look at the review stuff because these are little tricks that they're going to throw in there. Then you would know where the cusp occurs, right? Always. You're always, yeah, they're going to give you, they're going to give you hints like that. Yeah. So they'll not to mention the fact that, guys, all right, so were I to take the derivative of this, what would I get? Well, I would get 2/3 x to the -1/3, which is the same as this, right? So where does the derivative not exist? At 0, right? So there's, right, Gold? Right, so if I take my derivative, this is where it's not going to exist, right? So that's another way that I would know that there's some value of that's not differentiable, right? So again, we're starting to see how all of this stuff is going to play nice in the pool, right? It's all going to play nice in the pool, and all these things that we've been sort of hammering, all these little details, right? They're going to come into play, right? So we're going to keep reviewing on the stuff all year long, which is nice. Yeah, I'm not going to do this today. Well, I'm going to stop there. All right, I'm going to give you guys some time to